Alright, welcome back. In this video, we're going to go over HNMR, or hydrogen nuclear magnetic resonance. Now, HNMR tends to be a very challenging topic for a lot of students, but I promise you, as long as you follow these 4 steps, which I'm going to teach you, you can solve any HNMR problem. It's actually really easy. Okay, so what is HNMR first? Hydrogen nuclear magnetic resonance. Uses magnetic fields to determine the position of protons, and actually you can determine all the positions of all the atoms if you're an expert, but mainly protons. This works because protons have an odd number of protons in the nucleus. Whenever there's an odd number of protons and or neutrons in the nucleus of an atom, they observe spin. This spin is what is picked up by hydrogen nuclear magnetic resonance, and this can help us determine the positions of atoms. Now, fun fact, this is how MRI machines work. Magnetic fields excite protons found in water and fat in your body, and basically can be observed through a computer screen and scans and whatnot. So this is the third piece of spectroscopy you're going to learn. We did mass spec already. We did IR already. Now we're on HNMR, and the last thing would be CNMR, or carbon NMR, and that will probably be next video. So how do we interpret this junk here? To solve any HNMR problem, we need to go over 4 main characteristics. Number 1, how many signals are present in a molecule? Every standalone peak is a different signal. So this is known as a signal. This is a signal, and this is a signal. We have 3 signals here. What does this mean? Number 2, the location of the signals on the H-NMR graph can help us understand where protons are located. Why is this signal so far left and these other ones are so far to the right? Number 3, the area under the signals tells us how many protons exist in the compound. It is actually not written here, but when we get to that part, it's going to be super easy to understand. And number 4 tends to be a topic or characteristic that a lot of students get scared of. And honestly, it's not too bad as long as you know number 1. And this tells us the shape of the signals can tell us about neighboring protons. So, I'm going to be honest with you guys. Number 1 is the hardest one. If you can figure out number 1, you are home free for everything else about HNMR. Okay? It's just number 1. So let's do that. Number 1, how many signals are present in a molecule? So protons in a molecule can be located in different environments, or different electrical environments, or chemical environments. For example, we have a city here. We have hydrogens here on this house and hydrogens here. We also have hydrogens in the city. I could say these hydrogens in this, on the houses, are the same environment. The ones in the city are in the same environment to themselves, but the ones compared to the houses in the city are not in the same environment, right? We're in the suburbs here, and here we're in an urban environment, so different environments. So how do we figure this out? So over here on the NMR here, the Proton NMR, I could say this is environment number 1, this is environment number 2, and this is environment number 3. This is like saying this is the suburbs, this is the urban environment, and this is a rural area. To determine how many different environments there are, different environments a molecule has, we need to look at 2 things. One is the rotation, number 2 is the reflection. Now, I suggest you skip rotation. I do not have a good imagination, and maybe you don't either. So I really struggle with this. But if you're good at it, you can imagine the bonds like a toothpick. Imagine a toothpick. You hold the toothpick between your index finger and your thumb. You're able to rotate or spin around that toothpick. If you can imagine hydrogens that are attached to that toothpick, and when you rotate them, if they occupy the same average time in space when you rotate them, they're going to be in the same environment. Now, this probably makes no sense to you because it barely makes any sense to me, to be honest. So I just like to use symmetry. If there is symmetry in the molecule, the hydrogens can exhibit the same chemical environment. If there is no symmetry, the hydrogens will exhibit different chemical environments. So let's identify the different signals in this molecule. The first thing you need to do is identify all the hydrogens. So let's draw in all the hydrogens. This is the first step you need to do. Do not do this aimlessly. If you don't draw them in, you're going to be lost. And you're going to get it wrong. Because guaranteed you're probably going to miss one of them. Okay, so when we have methyl groups, I highly suggest you draw in the carbon. This is going to be very beneficial later on in the later steps. You'll see why. Okay. What this is right here in OME, this stands for methoxy. This is an oxygen bonded to a methyl group, okay? So I believe I have drawn in all the hydrogens. Now, here's the first thing you're gonna do. Anytime you have any methyl group, right? This is the trick. This is the cheat code. Cheat code number 1. Anytime you have a methyl group, all the hydrogens within that methyl group are gonna be similar to each other in the same chemical environment. They're all living in the same house, okay? So what you like to do, what I like to do, is draw a bubble around all those hydrogens in the methyl group. Okay? Let me make that neater. Okay. There we go. Now, CH2s, so hydrogens within a CH2 tend to be chemically similar to each other. So the hydrogens within it, right? So this is CH2. This is pretend like a house. These hydrogens are going to be chemically similar to each other. The case is not if there's a chiral carbon next to it, then the case would be no, they are not. But there's no chiral carbons anywhere here, so we're safe. So we can bubble in these ones together. Okay? Now circle the individual hydrogens. And now we have a methyl group here. So let me just draw in what we have here. And since I said methyl groups have their own environment, we circle this. Perfect. Okay, now you will notice this molecule has symmetry. If I were to do a karate chop, take a katana and to slice this molecule in half neatly, you would notice the left-hand side matches up with the right-hand side. So any molecules that look similar to each other on the left-hand side are going to be in the same environment on the right-hand side. So here's what I like to do. I like to draw a dot in the bubble and draw a connecting dot to the same environment. So the two methyl groups, since they're symmetrical, are going to be in the same environment. Same with this CH2. We have this one. And this is going to join with this one. These two CH2s are in the same environment. So is this hydrogen here with this one, because it's symmetrical, right? If you're symmetrical, right, down the middle, this one matches up with this one. This hydrogen is not symmetrical with anything. It's not symmetrical with this methyl group. They're not the same group. So this is going to be alone. This is going to be alone. And these hydrogens are not symmetrical with anything, so they're going to be alone as well. So now we count up how many similar environments we have. So we have, these are similar, so that's 1. These are similar, so that's 2. These are similar, so there are 3. This is alone, so this is 4. And this is alone, so we have 5. So we have 5 chemical environments, or 5 signals. 5 signals. So this means on an H-NMR graph, you would have 5 peaks, okay, wherever they would be located. Let's do another one. Draw on the hydrogens. So I draw this carbon. Okay. So once again, I said all the methyl groups, the hydrogens within the methyl group are all similar to each other. So you bubble that in. Bubble this in. Now, since we have no chiral carbons, we are A-okay to circle these two. Okay? Now, this molecule is not symmetrical, right? If I were to chop this down the middle this way, This is not symmetrical because of the bromines. There are no bromines on this side of the molecule, right? If I were to draw, a line down the middle, right? We have bromines here, but there are no bromines here, so it's not symmetrical. We cannot cut it this way either. It's not symmetrical. It would not work out. So we have different environments, completely different environments, because this molecule is not symmetrical whatsoever. So we count up all the pink circles that we have. So I should say we have a dot here, dot here, dot here, dot here. Okay, nothing, no equivalent in signals, right? No equivalent environments. Everywhere has their own signal. So this is 4 signals because we have 4 different bubbles. 1, 2, 3, 4, and none of them are joining. Let's do this one. This one we have a carbon, hydrogen, 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 hydrogen. Oh my god, hydrogen, 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 and hydrogen. Okay, once again, circle in the methyl groups. We have no chiral carbons, so we're okay. A-okay to circle these. This is alone, because this is not a methyl group, right? These 3 hydrogens here are not a methyl group. This is alone. Now, be careful here. You think that these hydrogens are related to each other, but they are not. The reason is because one of them is cis and one of them is trans, the main molecule. This hydrogen is actually in a cis conformation, and this is the trans. Now, if this is too complicated, what I suggest is think about it like if you see a double bond here, most of the time, they're going to be different environments. Okay? So, we circle this and circle this individually. This means, and we have no symmetry whatsoever in this molecule. So that means that all the circles are going to remain as it is. No joining groups. So you have 1, 2, 3, 4, 5, 6, 7 signals. Okay? Sweet. Here's our challenge problem. Escarvone. Probably seen this before because I've shown in videos in the past. I'm going to give you a hint here. This molecule has 10 signals. Now, I want you to pay very close attention because your professors will try to trick you like this. We have a chiral carbon here. This is chiral. So I am going to box this in for later. So let's draw in all the hydrogens. Sorry, I have my notes here just in case. I don't want to make a mistake for you guys because this is going to be a long video. Okay, when you draw in the hydrogens next to a chiral carbon, draw them with wedges and dashes. This is the trick. Tips and tricks, people, okay? Okay, and then we have a hidden one right here. Art school. Okay, and then we have one coming here and here, and then we have a CH. Okay, first thing as always, circle all the hydrogens within a methyl group. This. Okay, now, this is where, actually, let's do this part here. These are going to be individual because we have a double bond. That's the trick, okay? That's the best way to tell you, okay? Now, this is going to be alone because it's part of a chiral carbon. Now, these hydrogens here, part of these carbon, this carbon right here and this carbon right here, okay? Since it's adjacent to a chiral carbon, right? This is the chiral carbon right here. It's neighboring it. Since this carbon neighbors a chiral carbon, all the hydrogens attached to that adjacent carbon are going to be individual signals. They will not be the same. Okay? That's the trick. And then this one's going to be alone because there's no one else to match it up. So if I did my math right, let me make sure I have all the signals here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sweet. There we go. That's all of them. So once again, if you see a chiral carbon, any of the hydrogen that's attached to that chiral carbon, number one is going to be its own signal, and any hydrogens one carbon over from that chiral carbon will have its own individual signals. These are not going to be linked up. Okay? So they're all going to be individual. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 signals. Okay? Let's do number 2 now. Characteristic number 2. The location of the signals on an H-NMR graph tells us and helps us understand where protons are located. The further left we are, we call this downfield or deshielded. The further right we are upfield or shielded. Now notice the numbers are backwards. 8 is on the left and 1 is on the right hand side. It's not 1, 2, 3, 4, 5, right? It's 8, 7, 6, 5, 4, 3, 2, 1, right? Now, I want to tell you the quick 10-second explanation. If protons are located near an electronegative atom, they're going to be more to the left. They're going to be more downfield or more deshielded. If they are far away from an electronegative atom, which electronegative atoms are like oxygens, fluorines, bromines, all that kind of stuff, right? So if they're far away from them, they're going to be located more upfield, more shielded, okay? Now, here is something you need to remember. Something you need to remember. So here we have the locations of where on the graph these environments are going to be. How do we figure this out? So you'll notice that we have a chlorine here, right? You'll notice that these hydrogens here are very close to a chlorine atom with a 3.3 compared to these hydrogens, which are kind of further away at a 1.6 from the chlorine. 3.3 is closer left, right, than, right, we have 3.3 compared to like 1.6, right? It's because the chlorine is closer to these hydrogens. So more closer to the electronegative atom, higher the number, okay? Now, something else you need to know. You need to know something called the alpha carbon, beta carbon, gamma carbon. So the carbon that is right next to the electronegative atom we are looking at is known as the alpha carbon. The one next to it is going to be the beta one. And the third carbon away from that chlorine is going to be a gamma carbon. Now, we have to do some math here. It's not too bad, but there's something you need to remember. If you have a CH, so carbon and one hydrogen, remember 1.7. This is a default number. This is called methane. Methylene is 1.2. This is a CH2. A methyl, which is, CH3, our usual CH3, has a 0.9 ppm. These are default numbers you must memorize. If you want to get 100% on your HNMR test questions, remember these. It's going to help you. I promise you it's going to help you. Okay, this looks complicated, but really is not. What this is saying is if you have the functional group of an oxygen, so basically an alcohol or an ether, right? So an OH or an oxygen, right, with a carbon here, right? What you're going to do is you're going to take whatever number you see here, you have here, and add 2.5 to it. So let's show you an example here. We have a carbon right here, right? This is the alpha carbon because this is one carbon away from our electronegative atom. So this is the alpha carbon. We have a CH2 here, right? So we look at the CH2. This is a methylene group with a 1.2. So all you do is write down 1.2 plus 2.5 because this is an alcohol, and we get 3.7. So this is going to be this group, these two hydrogens here is going to be located 3.7 on this graph right here. So around like here, you would see peaks here. Okay, it's not too bad. Now, let's look if it was an oxygen of an ester group. So if it's a ester, so a carbon double bonded with an oxygen and a single bonded oxygen to that carbon, what we're going to do is we're going to add 3 to it. So this right here would be the alpha carbon. This is a methylene group. So since we're at an alpha carbon, so we have a methylene group, which is a 1.2, right? According to this, what I wrote down, a 1.2. And since we're next to an ester, we add 3. So 1.2 plus 3 equals 4.2. We would see signals at 4.2 on the graph. Well, carbonyls. So this is just simply a carbon bonded, double bonded to an oxygen. It's like this, but this has an extra oxygen, right? So all we have to do is add 1. So this is the alpha carbon. We have a methylene group, so we have 1.2 plus 1 is 2.2. Now, there is something called the beta carbon, like I talked about. What happens if the group was 2 spaces over? Right? So, for example, this is a methylene group, and we have a chlorine here. This is 2 spaces over. 1 hop, 2 hop, right? You'll notice that these numbers are for the alpha carbon. If you have a beta carbon, if you're looking at it from a beta carbon, your hydrogens are on a beta carbon, divide this number by 5. Simply, that's all you do. So this is going to be 0.5, this is 0.6, and this is 0.2. Now, this is a little confusing to you. Don't worry. We're going to do an example problem. Identify all the chemical shifts for every hydrogen environment. All right. So here's what you need to do. Write down all the hydrogens once again. This is going to be a theme, okay, for this video. This is why we draw in the carbons, by the way, because you need to know what the alpha carbon is and beta carbon is. If you just draw, let me give you a really good example here, because a lot of people make this mistake on exams. People think, right, that there's no carbon here because he didn't draw it in. People don't think. They just think there's hydrogens here. There's a carbon here. And this is going to screw you up. So that's why you draw it in. You don't know how many people have made this mistake. I've seen this people. You wouldn't believe how many people I've seen make this mistake. English. There's one here. Okay. So, what do we do? Let's look at this methyl group first. We are 1 hop, 2 hops. Sorry, wait. Yeah. Back up. I need to say something before we start this. I want you to pay attention because this is a very common mistake someone's going to make. Do not count this as the alpha carbon. This is a functional group. You do not count the carbon in the functional group. So what you think, right, is we have an oxygen here, right? This would be the alpha carbon, this would be a beta carbon, and then this would be a gamma carbon. This is not true. This would be incorrect. You skip whatever's part of the functional group. If the carbon is part of the functional group, you skip it. Do not count it. So we have a carbon here that's part of the functional group. So we do not count that when we count carbons. So we're going to look at this, right? From this carbon, technically it is from the oxygen, right? But this is part of the functional group. We go 1 carbon, 2 carbons. So this would be the alpha carbon and this is the beta carbon, okay? Methyl groups have a number of 0.9, right? So 0.9, so you have to do some math here. 0.9 plus, now we're at a beta carbon of a carbonyl, okay? So carbonyl we're not at a alpha carbon, we're at a beta, right? This is the number for an alpha, this is the number for a beta, 0.2. Right, 1.1. So we would expect to see these hydrogens at 1.1. Okay? This is going to be it's going to be similar, same number, because we are 1 hop, 2 hops, right? So this is the beta carbon right here. This is why we draw in the carbon here, because you're going to forget. You would think this is 1 hop and then the hydrogens, right? That would be just like the alpha carbon. Would that be incorrect? So this is also 0.9, because it's a methyl, plus, what did I say, 0.2, 1.1. Okay? Now, this is different. This is different. So we have 1 hop, and that's it. There's no carbon here. So this is an alpha carbon. So what we do is we have a CH, so it's 1.7. 1.7 plus, you have an alpha carbon at a carbonyl. So this is plus 1. 2.7. Okay, so we would see this hydrogen at 2.7 on that graph. So now let's do this one. Let's do this one. This one, this carbon's alpha to this oxygen. So we do 0.9 plus 2.5, because oxygen of an alcohol or an ether group is 2.5. This is an ether group because you have a carbon here and a carbon here. So this is an ether group. 3.4. Sweet. Okay, what about this one? Now, here is where it gets a little interesting. What do we do? This is going to be alpha to this oxygen, but beta to the carbonyl, right, to this carbonyl. So what do we do? So we have a CH2. CH2 equals 1.2. 1.2. Now we're alpha to the oxygen, the ether group. So that's 2.5. And now we are beta to a carbonyl. Beta to a carbonyl at 0.2. Seven, 8, 9.3, 3.9 ppm. Okay, so that would be for this. That's a terrible arrow. Okay, now what about this one? This is alpha to the carbonyl. Alpha to the carbonyl, and beta to the oxygen. And beta to the oxygen. So we have a CH2. So once again, we go back here. CH2 is 1.2. Alpha to a carbonyl. So we have a carbonyl. Alpha is plus 1. And then we're beta to an oxygen of ether. So 0.5. 2.7. Okay, and that's it. These are all the signals. And the shifts. It's not too bad, right? Now, gamma carbons, there's nothing. It's too far away. So if the hydrogens are 3 carbons away from a functional group, they don't matter. They don't count. They have no influence. The electronegativity have no influence because 3 carbons is too far away. That's the rule. If you see peaks around 7, you most likely have a benzene. This is just additional information, just in case. A ring or a benzene, I should say. Let's do number 3. It's very, very easy, actually. The area under the signals tells us how many protons exist in a compound. So you'll notice on sometimes your professor will give this to you, or a book problems, or something called integration values. You'll notice values below peaks here. Okay? Sometimes you will see curves like this. Here's my tip. The curves are garbage. Do not look at them. They're just there to confuse you. Okay? I hate them. They're useless to me. Okay? Here's how you do it. You use the integration values that they give to you. Here's what you do. It's very, very easy to solve. All you need to do is find the lowest integration number, divide all the integration numbers given by that lowest integration number you found, and then multiply by 2. So let's do that. Here, ignore everything else. Ignore everything else here. You'll notice that we have 27, 40.2, 28.4, and 42.2. 27 is the lowest. Okay? So what we're going to do is we're going to take 27 divided by 27, right? Because this peak corresponds to 27. So we're going to put 27 in the numerator, and since 27 is the lowest number, we put that in the denominator and we get 1. Then we take 1 and multiply by 2. So we get the final result as 2. Here we have 40.2. So what we're going to do is you put 40.2 in the numerator divided by the lowest number, which is 27, like I said. We get 1.49. Then we multiply by 2 to get 3. We round up. You either round down or up, whatever it makes it a whole number. Here we have 28.4. So what we either do is we put 28.4 in the numerator, then put the lowest number we found, which is 27. We get 1.05. Take 1.05 and multiply by 2. Then we have 42.2. We take 42.2, put in the numerator, put 27 in the denominator because that's the lowest. We got 1.56. 1.56 times 2 is 3. Now, what are these numbers that I boxed in? These numbers are telling you how many hydrogens are actually physically there. So we have 2 hydrogens here for this peak. We have 3 hydrogens here. We have 2 hydrogens for this peak. And we have 3 hydrogens for this peak. The number of peaks you see here do not tell you how many hydrogens there are. Do not be fooled. That is not what it's telling you. That's a completely different thing, which is going to be the next part. Now, the reason you multiply by 2 is because you cannot have half of a proton. That does not make sense. So the reason we multiply by 2 is so we can get whole numbers. Okay? It's pretty easy, right? There you go. So now number 4. This tends to be a very scary part of it, but it's really easy. The shape of the signals tells us which the shape of the signals tells us about neighboring protons. This is called multiplicity. Multiplicity tells us how many individual peaks there are to one signal, and the peaks tell us how many neighboring hydrogens there are. So this, if you have 1 peak, this is called a singlet. 2 peaks is called a doublet. Triplet. Quartet is 4 peaks. Quintet is 5 peaks. Sextet is 6 peaks. And septet is 7 peaks. There's a very easy cheat code to do this. All you need to do is look at an environment and count all the adjacent protons that are either 1 carbon away or 2 carbons away. Take that number and add 1. That is the number of peaks. If the hydrogen you are counting, I not spell today, but if the hydrogens you are counting are in the same environment, they do not split, so you do not count them. So let's do an example. All right, example problem. Determine the multiplicity of each signal. So the first thing you do is draw out the carbons and hydrogen. Okay. Okay. That's all of them. So let's take a look at this this proton right here. How many neighbors does it have that is one carbon or two carbons away? So we have carbon here, right? So this is one carbon and two carbons. So there are three protons here, and then so if we go in this direction, we have one carbon, two carbons, and three protons here. This proton has six neighbors, six protons that are neighbors, because they are within. I should say, let me rephrase it like this. There are six protons that are within two carbon atoms away. Okay? So we have, so this proton has this neighbor, this neighbor, this neighbor, this neighbor, this neighbor, this neighbor. Six. So here's what you do. We have six neighbors. What you do is add one to that. So let me write it in. So we have six neighbors plus 1 equals 7. And this is known as a septet. The reason this is called a septet is because we added 1. Right? So we take the number of neighbors and add 1 to it to get 7. And this is called a septet, right? Because septet is 7. Okay? What about this one? What do we do here? This methyl group is all 1, right? It's all one environment that has 1 neighbor. And then you'll notice that this carbon is too far away, right? Because we have a hydrogen here, right? So we go from 1 carbon, 2 carbons, 3 carbons. 3 carbons is too far away. We can only be within 2 carbons. So, right, we go hop 1 and hop 2. So we only have 1 neighbor. So this signal right here has 1 neighbor. And this is a doublet. Is 1 plus 1. Same for this one. Because we start from the hydrogens, right? We have 1 carbon, 2 carbons, and we have 1 neighbor. We cannot go here because this is 3 carbons. So this is the same thing. 1 neighbor, doublet. Sweet. What about this one? Okay, so we have carbon here, carbon here, carbon here. Starting from the hydrogens, we go 1 space, that's 1 carbon, and 2 carbons. We have 2 protons here in the vicinity. There are no protons here. So this is going to be 2 neighbors, also known as a triplet. What about this one? We start from the hydrogen, right? So start from the hydrogens, 1 carbon, 2 carbons, nothing in the vicinity. So we go the other direction. 2 carbons, we start from here, right? Let's start from here. 1 carbon, 2 carbons. We're in the vicinity of 2 protons. So this is going to be 2 neighbors, also known as a triplet. Okay, what about this one? Start from the hydrogen, we go 1 carbon, 2 carbons. Now, what do? We have no neighbors. We have no neighbors, right? No neighbors within 2 carbons, right? Because we go from here, 1 carbon, 2 carbons, no other neighbors. So this is just going to be a singlet. Same with this one. And same with this one. And that's it. Not too bad, right? So we will see these peaks, right? So this right here, triplet, right? That would be a triplet. This is a singlet. That's what you would see. All right, complex splitting. This is honestly, you want to kill yourself, honestly, because complex splitting is awful. But What happens if an environment is being split by multiple different environments? Simply count the hydrogens in each environment separately, then multiply the numbers. So, let's look at all the different environments we have, all the fun environments. So we have this one, we have this one. By the way, there are the letters there, so it makes it easy, but I plagiarized this. So, 4 different environments, right? So we're going to look at HC, which is the yellow one. You'll notice it is being split by 2 different environments here. This one has 2 protons, right? Protons. This one has 3 protons. 2 plus 3 is 5. And since we add 1 to that, that is a sextet. So we have 5 neighbors. And this is a sextet, because we add 1. Okay? This is a sextet. So we do see a sextet. 1, 2, 3, 4, 5, 6, right, for HC. Now, it is called something different, though, because it is being basically split by 2 different environments. What do we call this? So, what we do is we call this, so first we investigate all the different environments. So if we have 2 protons here, so this is technically called a triplet. You have 3 protons here, so this is called a quartet. This is called a triplet of quartets. That's the name of it. Okay, that's the actual name of this peak. We do not call this a sextet. Even though it looks like one, we call this a triplet of quartets. Now, there's a way, how do you know if it's called quartet of triplets and triplet of quartets? There is a difference. That's very complicated because it involves some math. But typically, usually the bigger group gets called first. But don't worry about it, okay? Just take my word, it's triplet of quartets is the answer, okay? If you found this video helpful, please like and subscribe. I'm going to do some practice problems after this, probably the next video. But if you found this guide helpful, please like and subscribe. Until next time, later.